Somewhere right now, matter is undergoing something unimaginable. Substance can be compressed to such an extent that it ceases to be what it always was. Worlds inside atoms collapse, electrons disappear, neutrons collide into terrifying shapes. In everyday life, we encounter pressure only in car tires or weather barometers. But this is just a simple game compared to what happens in the depths of planets, in the hearts of dying stars, and possibly in black holes. At first glance, it seems that any substance has a strength limit. Metal has fluidity, diamonds have cracks, and atoms have limits. But science is increasingly encountering facts that blur these boundaries. What if pressure can grow indefinitely? What if, instead of breaking down, matter is restructured, mutates, and opens up new forms of life? And this is where the journey begins, where everything familiar literally breaks down, where quantum fields surrender to gravity, where atoms turn into hyper-exotic particles, where even space and time no longer recognize themselves. Pressure is not just a force, it is an opportunity to look into the hellish forge of the universe, where its most insane forms are born. Try to imagine a giant mountain weighing 1,000,000 tons pressing down on a surface the size of a fingernail. That's what 1 gigapascal feels like. Pressure that is only found in laboratories and in the depths of planets. But that's just the beginning. Pressure is not just a physical quantity, it is an absolute predator that endlessly strengthens its grip, blurring the line between matter and its end. It all starts with the familiar pascals. 1 pascal is a negligible force. Already 100,000 pascals, or 1 bar, is the atmospheric pressure at the Earth's surface. But in the world of high energies, this is not even a warm-up. When it comes to gigapascals and megabars, we are talking about loads that break molecular bonds and cause matter to transition into unfamiliar phases. 1 bar is equal to 100 gigapascals, and it is at this point that the real battle with matter begins. 1 pascal is the pressure at which hydrogen, the lightest element, can transition into a metallic state. Such numbers are a physicist's dream and an engineer's nightmare. 1 petapascal is the pressure at which atoms lose their meaning, merging into dense plasma. And somewhere beyond the horizon of theory looms a value that even language calls a sapascal. A sapascal is 10 to the 21st power of pascals. This is already an almost mystical zone where our models begin to crack at the seams. To measure such monstrous pressures, scientists have invented something special, a diamond anvil. This device uses two perfectly polished diamonds to compress a sample to fantastic densities. With its help, pressures of up to 495 gigapascals have been achieved, and in 2023, it was announced that more than 477 gigapascals had been sustained while studying metallic hydrogen. But further on, everything becomes more complicated, and even diamonds give up. Scientists are turning to laser compression, shock waves, magnetic shock waves, and every possible method to look beyond the edge. And what do we see? With each step, the pressure reveals a new secret. In the laboratory, it is a challenge to materials, and in the depths of stars and exoplanets, it is a new form of the universe itself. Pressure is not just a force. It is a tool with which the universe creates the impossible. We are all accustomed to the idea that the Earth's core is something solid, hot, and heavy. The pressure there reaches about 360 gigapascals. And that already sounds impressive. But in space, there are objects that seem to have been created specifically to confuse us completely. These monsters exert such force that atoms themselves cannot withstand it and literally cease to exist. Imagine a star that has exhausted its nuclear fuel, exploded as a supernova, and left behind not ashes, but a terrifyingly compressed core. This is a neutron star, an object compressed to a size of only 20 to 25 kilometers. It's like cramming Everest into a teaspoon. What happens inside such a star? The pressure there reaches 10 to the power of 34 pascals, or 100 trillion gigapascals, which is millions of times higher than any possible limit on Earth. At such values, familiar matter disintegrates. Electrons are literally pressed into protons, turning them into neutrons. All matter becomes a neutron soup, monstrously dense and almost indivisible. Individual atoms disappear. The periodic table no longer works. Even quarks, more fundamental particles, can begin to behave collectively, merging into exotic forms of matter. And if that's not enough, what scientists call nuclear paste can form in the depths of neutron stars. This substance has the most bizarre shapes, resembling lasagna, spaghetti, or bent pipes. What is the reason for this, you may ask? The balance between strong nuclear interaction and gravity gives rise to incredible structures with a density 10 to the power of 10 times greater than water. And if the star was even more massive, it would not even stop at the neutron star stage. It would continue rolling down the slope and turn into a black hole. But there is one caveat. What is the pressure inside a black hole? From the outside, we only see the event horizon, the point of no return. Everything inside is hidden from us behind a veil of gravitational darkness. Theoretically, all mass is compressed into a singularity, which means infinite pressure. This is where physics ceases to work. Quantum theory is powerless. General relativity breaks down, space and time collapse. We don't know what's inside, but we know there's more there than at any other point in the universe. Some scientists suggest that at the edge of the singularity, the pressure can reach 10 to the power of 30 pascals and above, up to values at which even quarks cease to exist as separate particles. This is no longer just force, it is an abstract monstrosity, physically impossible in our reality, but quite possible inside these dark objects. Conclusion. If we tried to simulate even a fraction of these cosmic pressures on Earth, everything we know would disappear. Diamonds would turn into liquid, iron would spread like oil, atoms would flatten, electrons would disappear, and space would begin to bend in on itself. But in the universe, all this is already happening. Where there is no starlight, no oxygen, no meaning in molecules, there is only pressure, merciless, unstoppable, and boundless. As soon as we start compressing an atom, reality begins to change. Atoms are not that strong. Pressure is not just a threat. It is a tool that can destroy the very architecture of matter. Under normal conditions, atoms look like light structures where electrons swirl around the nucleus. But if you start to increase the pressure to hundreds of gigapascals, everything changes. Electrons are no longer simply in their orbits. They begin to feel the walls closing in. The electron clouds become denser, overlap, and atoms literally begin to merge into each other. In the early stages, this causes phase transitions. Metal becomes a superconductor. Insulation becomes a conductor. A classic example is hydrogen. At a pressure of about 400 to 500 gigapascals, it loses its molecular structure and transitions to a metallic phase, where electrons are no longer bound to specific atoms but flow freely, like in a river. At even higher pressures in the terapascal range, the most frightening part begins. Electrons begin to be pressed into the nuclei. The pressure becomes so tremendous that it no longer acts only on the orbital, but attacks the very essence of the atom. Under such conditions, inverse beta decay occurs. An electron plus a proton, then a neutron plus a neutrino. And so protons disappear, electrons disappear, only neutrons remain. Matter turns into a homogeneous neutron soup. This is what a neutron star consists of. I have already talked about this before. And if before the atom was an individual, now it is just a point in a huge collective body of neutron mass. But is there a limit? What happens after neutrons? Some scientists believe that at even higher pressures, above 10 to the power of 36 pascals, even neutrons can break down. After all, it consists of quarks, and quarks are held together by strong interaction. What if even they succumb to pressure? This is how the theory of quark matter emerges. Neutrons break down into their constituent quarks, and these form quark plasma. This is a completely new state of matter, almost mythical, but highly probable inside the cores of neutron stars or in conditions preceding the formation of black holes. And then there are the supposed strange stars and strange matter in which strange quarks are involved. In this state, matter becomes denser than anything we know, and at the same time completely alien, almost incompressible. It is capable of infecting ordinary matter, turning it into strange matter upon contact. Everything we call chemistry, physics, and logic dies under such pressures. Electrons lose their individuality. Nuclei are no longer the center. Quarks begin to form not proton or neutron systems, but global fluctuation structures. This is not just compression, it is the destruction of the concept of a particle. Where pressure exceeds all possibilities, matter ceases to be substance in our sense. It becomes a physical conglomeration of interactions, intertwined fields, where even space begins to lose its stability. In 2022 and 2023, experiments were conducted using a new generation of diamond anvil cells, where the pressure reached 495 gigapascals, and at the same time, it was possible to stabilize hydrogen in the metallized phase. This means that atomic restructuring is not a theory, but a reality. We are already on the threshold of pressures where the familiar dies. Is it really possible to increase pressure indefinitely? Or is there some final frontier, an absolute limit beyond which matter ceases to exist in principle? At first glance, it seems obvious. Everything has a limit, but physics, as always, is on its own wavelength. There are natural pressure machines in the universe. Gravity. The more massive an object is, the more it compresses itself. First, there are white dwarfs, where electrons are almost squeezed into nuclei. Then there are neutron stars, where all matter is already a collapsed ocean of neutrons. And then there is silence. Gravity continues to press. It knows no mercy. The path to a black hole begins. Formally, according to the equations of general relativity, a black hole collapses into a singularity, a point with infinite density and accordingly infinite pressure. Mathematics says the limit has been reached, beyond that is absurd. But physics does not give up again. To what limit can matter go before it disappears as such? Modern calculations show that at pressures above 10 to the power of 30 pascals, which is close to the state of a neutron star, protons and neutrons can melt into what is known as quark-gluon plasma. This is something between a liquid and a field, where there are no longer any separate particles. But even that is not the end. What comes next? New exotic states such as strange matter, colored supercondensates, topological vacuums, or even nature's rejection of matter as a form. Formally, a singularity is a flag that science plants on the frontier of knowledge. But more and more theories, including quantum gravity, loop gravity, and string theory, suggest that singularity does not exist. Instead of infinity, there is something else. Perhaps space bounces off the boundary, giving birth to a new universe, or matter transforms into a form that we are not yet able to imagine. And this is where it gets scary. Pressure may not be infinite, but its limit is no longer about matter, but about the boundary of reality itself. Perhaps it is in this limit that the ultimate mystery is hidden, where space, time, matter, and energy merge together. And there, beyond the limits of pressure, we will find not the end, but the beginning of something greater. Is it possible to lift the veil on the secrets of monstrous cosmic pressures, even a little, without leaving Earth? The answer is yes. For decades, scientists have been trying to reproduce the hellish conditions of the interiors of planets, the cores of stars, and even the birth of the universe. But what they find sometimes does not fit into the familiar picture of reality. At the forefront of these experiments is one simple tool, the diamond anvil cell. I have already mentioned it. It is a tiny device where a sample is compressed between two perfect diamonds. And if the normal pressure at the center of the Earth is about 360 gigapascals, then in the laboratory they have already reached about 1,000 gigapascals. For comparison, this is 10 million times higher than the air pressure above our heads. But this turned out to be insufficient. To simulate a supernova explosion or a collision of neutron stars, stronger impacts are required. This is where laser fusion comes into play. In one of the laboratories in the US, giant lasers strike a target with such energy that the sample experiences pressure above 1 terapascal and literally disappears as a substance, turning into plasma. That's not all. This is where the real miracles begin. Under extreme pressure, hydrogen, the simplest element, suddenly becomes a metal. It begins to conduct electricity like copper. Scientists believe that inside Jupiter and Saturn, there is metallic hydrogen, which generates the giant magnetic fields of these planets. On Earth, it was first recorded in 2016. How about iron, which suddenly loses its crystalline structure and turns into an amorphous liquid under incredible pressure? Or graphite, which turns into a super strong phase that surpasses diamonds? These experiments show that matter is capable of much more than we thought. Under pressure, new phases appear, unknown states, abnormal behavior. Some materials suddenly become superconductors at room temperature, as in the case of long hydride pressed to 250 gigapascals. Scientists hope that this could revolutionize energy. But behind all this lies an alarming conclusion. The deeper we delve into the nature of matter, the less it conforms to our expectations. Pressure is not just a force, it is the key to doors behind which physics becomes unrecognizable. You might think, so what if somewhere out there, in the depths of dead stars, the pressure is trillions of times greater than on Earth? How does that relate to us, to humanity, to our everyday reality? And here's the most interesting part. The technologies that shape the future can be born in these extreme conditions. Every time scientists raise the pressure to extreme levels, matter reveals new tricks. Some elements suddenly change their properties, becoming transparent, superconductive, and indestructible. And these discoveries are already finding their way into the real world. Super hard materials, such as new phases of carbon, are stronger than diamonds and can be used in space armor, microscopy, drilling into the interior of planets, or even in nuclear protection. Metallic hydrogen. If it can be stabilized at normal pressure, it could become the most powerful source of energy. Rocket fuel that is dozens of times more efficient than any known fuel. Hydrides have shown superconductivity at room temperature, but at pressures of about 170 to 250 gigapascals. Scientists are working to transfer this property to more accessible conditions. This will revolutionize energy and transportation. The Earth is not an empty sphere. At its center rages a red-hot iron ball, which is subjected to pressures exceeding 3.5 million atmospheres. Understanding the behavior of matter under such pressures helps us model the Earth's core, understand the magnetic field, seismic waves, and the behavior of tectonic plates. And if we look further, for example, to Jupiter, Saturn, and some exoplanets, modeling high pressures will lead to an understanding of entire worlds. Some planets may be completely covered with layers of ice compressed to a metallic state. In such oceans, life may exist in incredible forms. When we study how matter behaves at pressures close to the center of a neutron star, we are essentially modeling the evolution of the universe in the first fractions of a second after the Big Bang. This data is critically important for controlled thermonuclear fusion, antimatter projects, the study of dark matter and dark energy, and the development of high-energy lasers that can be used in space or even in medicine. Understanding matter under pressure already allows us to create a new generation of engines, heat-resistant shells, vacuum traps, and membranes for plasma confinement. All of this is a direct continuation of research in extreme laboratories. For example, new phases of superhard nitrides and borides are already being used for deep drilling, and unique metals obtained under high-pressure conditions could form the basis of space elevators or shields to protect against micrometeorites. In general, we are used to fearing pressure in both the literal and metaphorical sense, but in the world of science, it is precisely this that becomes the key to new evolutions of matter. Everything we know, stones, metals, even air, can reveal a completely unexpected side under the right conditions.